we define a complex function actually. Right, so it's a function from a subset X of the complex plane or the set of all complex numbers 2 to C. Okay, and so it's from X itself to find a suitable domain. So you have to, so when you look at a description of a complex function, then from the description you will be able to see what is the proper domain. Means that XX here for the F to be defined on. Okay, so examples. So probably, let me see. So if W is the, so we define a function with value W, which is, say example, a polynomial function. Okay, and so for this polynomial function is a complex function, of course, okay, defined the whole set of complex numbers. So this is quite obvious because when you put any complex number as C, you will find a specific value. Okay, so that would be not any problem. All right. Okay, and for this function, I let Z as X plus I1, and X is the real part, Y is the imaginary part. So so we can describe Fz by using X and Y. So this is X plus I1, 3 X plus I1. Okay, so we just do the substitution. So after some algebraic manipulations, you will see that this is equal to, right? So you can put all the real part here and the imaginary part here. Okay. Right, and we say this is, so in general, okay, in general, the real part of the value of the value of the function is a function of the real part and imaginary part X and Y of the independent value of Z. Okay, and this is V, this is Y. Okay, so okay. Right, so you can see that. All right, and so So we can write the function by using so this is the, so we can have that. The second example is f of z is equal to 1 over z. Okay. Now, so this is a complex function. Okay. Defined this set. So because z cannot be 0, okay, so except 0, we can put an arbitrary complex number here to get a value, right? So we know the domain is the whole complex plane by deleting the origin in the plane. Okay, and in this way, so W, Z. So here we have x plus I1, okay, and all right. So finally we have x squared plus y squared x plus I minus y s squared plus y squared. Okay. So the uxy becomes to x squared plus y squared, and the vxy becomes to minus y x squared plus y squared. And remember, because the domain, right, has is the domain does not contain 0, so the denominator cannot be 0. Okay, so this is what we'll define. Okay. Right. Right. So on the other hand, a complex function can be constructed, okay, by a pair of real functions u x y and v x y. Okay, and each depending on real variables x and y. Okay, so we can directly define a complex function by using a pair of real functions u x y and v x y. Okay. So example. Suppose we want to define a complex function, right? So we say we want to have x squared plus 1, and this is a square. So we know that so this is our ux1, and this is our vx1. So we have that. And from these descriptions that we know that actually we can put any x, any y here, right, to get a specific value. So you know that from this expression, you know that the domain actually is the set of all complex numbers. Okay. And so, well, we know the x actually is 1/2 of z plus z complete conjugate. And the y actually is z minus z bar by 2i. Okay? So we have this, can change, right? Because x is the real part of the complex number, and z, and y is the imaginary part. Okay? So actually, f of z becomes 2z plus z bar divided by 2 square plus z minus z bar 2i, okay, plus I, z plus z bar 2 minus z minus z bar 2i square, okay. So now you can see that we can express that the function, complex function, by using the z. Okay, because you know z bar actually is a function of z, right? Z bar is actually. For example, for here you can write this one as z square and then z bar, right? For example, this is the real number, right? And this is z bar. So actually you can convert such a definition into express the complex function in terms of z. Okay, so either way you can define complex functions. Any questions? Okay, so even though you can define complex function in a very generalized way, but some of the some function behaves not smooth as we expect. Okay, and so to study the smoothness of a complex function, we have to define derivatives of complex functions. So now, the derivative of a complex function f at an interior point. Okay, so now you know what is an interior point. Z of the defining domain. I have to be careful, the defining set of f. Okay, so we said the defining set of f means that the set that f can be defined. For example, for this function, the defining set actually is the whole set of complex number. And for this function, the defining set actually is the whole set of complex number, but it's good. You have to exclude 0 here. Okay. And we have to pick up an interior point z0 because we need to use a neighborhood, all right? Because if z0 is so as we say that, and suppose this is our defining domain, and this is z0. If z0 is an interior point, it means that we have a neighborhood. Okay, so we have a neighborhood. So this neighborhood is contained in S. Okay, so we have a neighborhood contained in X. Means that the f function has value at each point in the neighborhood of z0. Okay, and we need that value, those values to define the derivative at this point. Okay, so now it's an interior point z0 of the defined set of x is defined. Okay, so this is our definition. It's defined to be, alright, so it's defined to be here. Okay, provided that this limit, I will have a space to write down later. So provided that the limit exists. Okay. So provided that this limit exists, so we have a difference of the function value divided by and a small, actually a small complex number. Of course, this complex number cannot be equal to 0, but will approach to 0 anyway. So as z goes to 0, then z0 plus delta z actually is in this neighborhood. And we need it is defined in this neighborhood. F is defined in this neighborhood, otherwise you cannot have a value there. Okay, so that's important. And another way is to describe that. By linking at the delta 0 actually. So here we define z is z0 plus delta z. Okay? So that means that delta z is z minus z0. Okay? So we have that. Either you put in this way or in this way. Okay? So we say that we have a derivative of function f at the interior point z0 if this limit exists. If this limit does not exist, then we will say that such a derivative does not exist at z0. Okay? Alright, so let's see. Okay, and so we look at so here, so this is z, right? So z goes to this 0, maybe from here, so another kind of z goes here, or from here goes to 0. Okay, so z goes to 0 from everywhere, but very near to z0 means that the z is in a neighborhood, but anywhere in this neighborhood should be true. Okay? True. All right. And in this case, so in this case, f is said to be differentiable. Okay, at z0. Okay, at z0. The reason why we hard to define derivative at boundary point is because that if z0 is on the boundary of x, then so suppose you have boundary here. Suppose this is z0. Then any neighborhood contain points, right? Contain points. This is Z, right? Right, and F may not be defined as we see. Okay? May not be defined. Okay, may not be defined. So it is very hard to say what is the limiting process, right? The difference between Z and Z0, okay? Because for some delta Z, this is undefined. You have no value, so you cannot find the difference in the numerator. So that's why it is usually required that when we say a function, a complex function is differentiable at a point Z0. The point Z0 should be an interior point of the defining set of the function. Otherwise, we have technical problem here. Of course, in some special cases, you can alleviate a technical problem. Sometimes, for example, if you know what exactly, let's say, for example, if you know the defined domain is in the first quadrant, say including the boundary, so suppose it's here, and you want to know whether a function is defined in X, okay, and you want to know whether the function is so-called smooth at the point. Well, you may say that the Z is in this corner, okay. Somehow, if you know that this corner, what is exactly this corner is, right? And then you are able to, so the Z here, okay, approach to Z0, only from this corner. Because outside this corner here, the function f may not be defined. Okay? And so it's possible that the limiting process, the limit may exist. May exist, special cases. But that is very special. Maybe you need that kind of definition in special circumstances. Okay? So in our general discussions, we just investigate the case in this student that Z0 is an interior point of the defining set. Okay, so let's take an example to find the derivative. So suppose it's a monomial and defined. So the defining set is the whole complex plane. Okay, and so we let Z0. Alright, so Z0, any point, is an interior point of the defining set. Okay, and so we try to find the derivative of f at Z0. Okay, so we just presume that the limit exists, but we try to find it. Otherwise, we are unable to do that. So we have okay, and this is Z0 plus delta Z square minus Z0 square. Right, so now the numerator we have 2Z0 delta Z plus delta Z square, and this is delta Z. Okay. And so now in the denominator we have a factor delta Z, so this factor can be cancelled with the the numerator has a factor delta z and can be cancelled with the denominator. So we have 2z0 plus delta z here. Okay? And this is a constant. And the second term will go to 0 as delta z equals to 0. So this is 2z0. So we find that for this function, this function has derivative at every point z0. Okay? And the value of the derivative is equal to 2 times z0. So we know that derivative exists, and we know what is the derivative function. Sorry. Okay, and a fact is that if f is differentiable at z0, then f is continuous at z0. Right? So whenever we see that a statement say f is differentiable at z0, it implies that z0 is an interior point of the defining set of f. So that means that f is defined or on a neighborhood of z0. Okay? So it implies, so maybe I will say, the statement implies, because when say f is differentiable, this statement implies that f is defined on a neighborhood of z0. Okay? So that is the understanding we have. Right? And so if f is differentiable at z0, then f is continuous at z0. Well, so the proof is here. So we may so that z be in a neighborhood of z0 where f is defined. Okay, so we use this implicit meaning. Okay, so that is the neighborhood. And so we can consider the difference. Okay, so when we consider the difference, and so that is okay, and the difference can be written as a product of this ratio times this term here. Okay? So we can, so now as z goes to z0, so we have for all z in a neighborhood not equal to z0, okay? And so the limit of the difference becomes to okay? Because as z goes to 0, this fraction has a limit. As z goes to 0, this fraction has limit. Okay? And so if these two vectors has limit, then the product will have limit, and the limit is equal to the product of their respective limit. But so, and this why is that? This is a plus, this is 0. Okay, because it exists, right? And why is that? As z goes to 0, this is 0. So the product is 0. Right? So the limit of the difference goes to 0 as z goes to z0. So we find that the limit z goes to z0 is equal to so this proves that if f is differentiable at z0, then f is continuous at z0. Okay, so this is the it's quite similar to the proof in calculus for real valued functions on real variable. Okay. Any questions? Any remark? Okay, we can express a complex function by using two real value functions on x and y, right? You know that. So, and we can say fz is continuous at z0 if and only if u x y and v x y are continuous at x0 or 0. So we say right. So if we have this convention, right, and we write the complex function in terms of u and v, then fz is continuous at z0 if and only if u, the real parts and the imaginary parts are continuous at this point. Okay, so I just skip the proof, okay? And this is quite similar to a function defined on the plane, okay? And so you have a vector function. So a complex function is just like because this expression, you can say that this is x plus iy, right? So you can think about a complex number is a two-dimensional real vector. And so you have a vector, right? You have a vector, xy vector, go to u, v vector. Okay? So it's a vector map, and from that you will see that because when we study functions of multiple variables, we have this expression. All right. An example. All right. A good example is that suppose we define a function. Okay. So this is function defined on the whole complex plane. Okay. So it's defined for all complex plane. Okay. So we let z0 in C. Alright? And we try to find the derivative of the function at z0. Right? And so we have z, 0 plus delta z minus f 0. We have z here. Okay? And And so this is what is that? This is z0 plus delta z bar minus z0 bar. Okay, and so this is delta z bar. See here. Now we have trouble. We have trouble. The trouble is that so suppose that suppose z delta z it's delta x. So now I'm sorry, I forgot to put limit. The trouble is that the ratio depends on how you approach 0. Okay, so suppose that suppose delta z is delta x. Okay, so delta z approach to 0 from, so suppose it's from the x-axis, the real part. Okay, and right, and so so in this case, the limit of delta x go to 0, and the delta z is delta x, delta z is delta x. Okay, so the complex conjugate, and you find that this is equal to 1, no problem, right? So when you approach to 0 through the real parts, the ratio, the limit of ratio is go to 1. Okay, but suppose delta z is I, delta y. Okay, from the imaginary part, then the limit I delta y go to z, I delta y bar I delta y. Okay, because of the complex conjugate, so this becomes minus 1. Okay, becomes minus 1. How about so you when you go to this way, or go this way, so this is delta x, then the ratio is 1. But when you go from here to there, you have delta y. The other way is from the diagonal term. So suppose you have delta x, x, say we from say okay, say delta plus I delta. Okay, so suppose delta z is equal to delta plus I delta. Okay, so limit delta plus I delta goes to 0. Okay, so that equivalent to saying that delta goes to 0, right? And to find the ratio is delta minus I delta. And here is delta plus I delta, right? Okay? And so the limit, what is the limit? Because delta can cancel, so you can 1 minus I, 1 plus I. So the limit becomes to what? Becomes to 2. Okay, and this is 1 minus I squared. So what is that? 1 minus I. So this, what is that? It's minus I. Yeah, it's minus I. Because this is 1 minus 2i minus 1 minus 2i. Yeah, so this is minus I. So when it's go this way, then the limit is minus I. So you have It depends. You can try many different directions and end up with what? With different value. End up with different value. And you will see this value can be any what? Any number on the unit circle. We can prove that. Very interesting. So you can try that from different angle, right? They are different, but they have absolute value equal to 1. Why? Because the absolute value is equal to 1. Okay. Right? You take S value is equal to 1. Alright? But the value can be any value which has magnitude equal to 1. Very interesting. So from we conclude f from z does not exist. Alright, so f from does not exist at any z0 in C. Okay? So this function is not differentiable at any point. No derivative. Okay? And it is, so this is a very special kind of, so it is not smooth at all. Okay? So this function is not smooth at all. Right now, a complex function fz is said to be analytic. Okay, in a domain. Remember, a domain is an open connected subset of this. Okay. So we say that a complex function. Okay. A complex function f of z is said to be analytic, right? In a domain. And in a domain, if fz is defined and differentiable, okay, at all points in that domain. You know, because domain is an open set, so any point in this domain is a neighborhood, all right, in the domain. This is the definition of open set, okay? The open set. So every point in a domain is an interior point, okay? So you have to know every point in a domain is an interior point of that domain, okay? Right, so we say this is analytic in a domain. Sometimes we say the function f of z is said, sometimes we say that, to be analytic at a point z equal to z0 if f of z is analytic in a neighborhood of z0. Alright? So when we say a complex function is analytic at a point z0, we mean that actually everything is analytic in a neighborhood of 0. You know, a neighborhood of 0 actually is a domain. Okay, it's open, right? It's open disk. So it's connected, of course. A disk is connected. Alright. So even though it just said analytic at a point, actually it means analytic in a neighborhood of 0. It just does not specify how big of this neighborhood, just a neighborhood. Maybe very, very, very small, very tiny, but it is a neighborhood. Okay? Okay, now, so we will categorize differential functions in the domain. Alright, so we're going to consider the famous Cauchy-Riemann equation. Alright, so we will write the theorem, important theorem. Okay. We call Cauchy-Riemann equation. Okay. So let a complex function is written by this way. In terms of its real part function and imaginary part function. And we say that this one so let's be analytic at the z equal to 0 at a point. Alright, so you have to refer to this definition. So we say this complex function is analytic at a point. Actually, we mean that it is analytic in a neighborhood of z0. Okay? Neighborhood of z0. Then at that point, z0, the first order partial derivative okay, the first order partial derivative of u and v okay, exists. Right? So u has two first order partial derivatives, u to x, u to y, right? And v has two first order partial derivatives, v to x, v to y, right? So in total we have 4 first order partial derivatives in total. So and we say that if f of z, this complex function is analytic at a point, then these 4 first order partial derivatives exist. Okay, at this point. Okay, maybe I will say x0, y0. Okay, maybe I put it in this way. It is more clear. All right, exists and satisfy. The following two equations. Okay, so it's u of x at x0, y0 equal to v of y at x0, y0 And the u of y, so use the positive derivative of u with respect to y at the point is equal to minus v with respect to x at the point. Okay, so we have two first order partial differential equations. Okay, all right. So analytic function, right? A function is analytic at a point. It's a sufficient condition to imply that we have the four first order partial derivative of u and v exist and satisfy these two identities. So that is the and this equation. So these two equations are called Cauchy-Riemann equations. So these are called Cauchy-Riemann equations. Okay, so they are called. Okay, so hence, if f of z is analytic, okay, in a domain, okay, D, then ux, uy, vx, vy exist, right, in D, and satisfy so we will say these equations as 13.1, 20.4.1. State that. So this becomes to indeed a differential system of two first order differential equations, because these two differential equations must be satisfied for all points in the domain D. Okay, and the proof can be illustrated by this diagram. So, so this is z, 0 here, and we probably start at z0 plus delta z. Okay, so we probably started here, and so because that. This is in the neighborhood of z0, okay? And it will be 0. And we will approach, because we know that the complex function is analytic, right? Already analytic at point z0. All right, so we will approach the derivative, because if the derivative exists, then you can approach from 0 to delta 0 to 0 from arbitrary paths, right? Anyway, right? You can just approach to 0 in arbitrary way. And we will select two special paths. The first path we call the path 1, is like this one. The other is a dash, represented by the dash. So we call this path 2. This one. Okay, so for case 1, we just go to z0 to the y-axis, and then through the imaginary part, and then through the real part. The second pass is we first approach to 0 from the real part and then the imaginary part. And so there are different orders for to do so. So now we have assumed okay, so we have assumed that f from z0 exists, right? So the limit exists. Alright, so this is our given condition. Okay, so this ratio exists, and the delta z can approach to this to 0 in an arbitrary way. Anyway, curve maybe very curve in a curve or in any path, ever. Okay. Now, so we let delta z to be delta x plus I delta y, okay, and then z0 x0 plus I y0, okay. So z0 plus delta z is equal to x0 plus delta x plus I y0 plus delta y. Okay, so this is our preparation. Okay. All right, and now the ratio. Okay, so we have u. Okay, we use the uv expression here to x0 plus delta x, y0 plus delta y, minus u x0. So this is the real part, right? How about the imaginary part? We have v x0 plus delta x, y0 plus delta y, minus v x0. Okay. Right. So we just express this numerator in terms of u and v. Right. It's just direct substitution. Alright, and delta z is equal to this point. Okay, so now bypass 1. Alright, so we let bypass 1, we let delta y goes to what? Go to 0 first. And then we let delta x go to 0, the second. Alright, so in this case, we will end up with the same limit, right? This is given. So f from z0 x right. So we let delta y go to 0, follow this space here, and then delta x go to 0, right? And then compare to 0. Okay, and so this is our what we will do. Okay, so this is what we will do. And now, so now, first of all, when delta y goes to 0, when delta y goes to 0, okay, go to 0. This is go to 0, right? This go to 0. So the denominator, right, it's delta x, you have delta x here. Alright, because delta y equals 0. And for here, we say if f of x is differentiable at the point, it is continuous at the point. And when it is continuous at a point, the u and the v function are continuous at that corresponding point, right? And so that as delta y goes to 0, it goes to y0 here. Alright, this is very important. And here u x0. And for here we have v x0 plus delta x and y0 minus u v x0 y0. Since, so we have to say, since the limit of as delta y goes to 0 of u x0 plus delta x y0 plus delta y, right? This one is equal to u x0 plus delta x and y0. And the limit delta y goes to 0, v x0 plus delta x y0 plus delta y. So when delta y goes to 0, it comes to by the continuity of u x y, u v x y, okay, in a neighborhood because in a neighborhood of x0, y0. Because we know the function, when we say a function fz is analytic at a point, it means that fz is analytic in a neighborhood. So fz is differentiable in the neighborhood. So fz is continuous in the neighborhood. And so the real part and imaginary part function u and v are continuous in this neighborhood of points in the plane. So the reason why when delta y equals to 0, the first limit always exists, no problem. The reason is u and v are continuous functions in the neighborhood of x0 and y. Okay? So this is the key reason. Okay, and this limit exists, okay? Because we know it exists. So that means that this limit exists. So right? And because this exists, so these two, and the real part actually is the partial derivative. So u x so this is the partial derivative by the definition. So this is partial derivative. Okay, so these two exist. And then the derivative can be written as ux x0 y0 plus I vx. Okay, so we know the connection between this derivative with the partial derivatives here. So all this is true because we have assumed that this term exists. Any questions? Okay, so by pass one, right? We know we establish that these two partial derivatives exist at point x0, y0, and we have this expression, and we have this identity here. Okay, all from this setup. Okay. And in the immediate steps, we use the fact that u and v are continuous functions in a neighborhood of x0 and y0. So we use continuity. Okay, we use continuity. Any questions? All right. And so now the second thing is we do postulate. Now, by postulate, right, delta x goes to 0 first, and then delta y goes to 0. Right? So we reverse the process, and so f prime z 0 actually becomes to okay. So again, this ratio is equal to this ratio, right? Now, when we let delta x go to 0 first, then the denominator goes to I times delta y, okay? Because delta y is fixed, right? And delta y. And for the numerator, by the continuity of u, if delta x goes to 0, then the function value goes to u of x0 and y0 plus delta y. And again, by continuity of v, as delta x goes to 0, then this is v of x0 and y0 plus delta y. Okay. So we apply the first limit here. We find that we have u x0 y0 plus delta y minus u x0 y0 divided by I delta y. Okay, this is I delta y. And here we have v x0 y0 plus delta y minus v x0 y0. And here is I delta y. Okay, so now we manipulate I cancel, right? Cancel. And the I becomes to minus I here. Okay. And so we have u, all right, at x0, y0. So minus I. And for here we have v and y at x0, y0. So we know this partial derivative exists at x0, y0, and this another partial derivative exists at x0, y0. And we also prove that this derivative is equal to the expression here. Okay? know this is equal to right? Compare with them, you will see that the two, because they are real part, must be equal. Okay? And the minus plus this one will equal to this one. Okay? So we conclude that is equal to and minus and this is our Cauchy-Riemann equations. Okay, so they are all necessary conditions. Right. So once we know a complex function is analytic at a point, then we know we must have this four first order partial derivatives at the point x0, y0. And these four first order partial derivatives satisfy these two equations. Okay? Any questions? Right, so this, now we will state that the Cauchy-Riemann equation are also sufficient conditions. Okay, so we will state in another theorem. Let u x y and the v x y, okay, be two real values. Alright, so let u and v be two real valued functions of real variables x and y, which is continuous. Okay, so which is continuous, okay, which is continuous. Let's say which is continuous first order partial derivatives. U x, u y, v x, v y. Okay, so these four first order partial derivatives are continuous, right? satisfying in a domain E, satisfying the Cauchy-Riemann equations. Okay, in B. Right. So first of all, suppose we have two. As we know, we can construct a complex function by two real value functions u and v, right? Of two real variables s and y. We can construct that, right? And now we require these two functions u and v, right, have continuous first order partial derivative. Okay? So they should have continuous first order partial derivative in a domain D, domain D. And these four first order partial derivative satisfy the Cauchy-Riemann equations. Okay, the Cauchy-Riemann equations. Right. Then the complex function f of z defined by uxy plus I vxy is analytic indeed. So the conclusion is very simple. Once we have such kind of two real value function u and v, if we have that, alright, and they have continuous. So the important thing is that they have continuous first order partial derivative in the whole domain D. And these four first order partial derivatives satisfying the Cauchy-Riemann equations. Okay. So we have to justify they satisfy the Cauchy-Riemann equations. If this is true, then the complex function defined by u and v, okay, is analytic indeed. Okay, and the proof is a bit complicated. So, but you can find a proof. Page 878 in appendix 4 of the textbook. So we need this theorem to construct useful and complex function, which is analytic, including the exponential function. Okay, including the exponential function. So and so it is very useful in applications, but it is also very important in theory because it gives you a kind of sufficient condition, right, of the u and v to construct an analytic function. And we will study a lot on analytic function. Okay, analytic function is in the central role of complex analysis. Right. So this is so this is a very constructive way, right, to construct an analytic function. Any questions? An analytic function has very nice property. For example, let me explain the fact. If f of z is analytic in a domain D, such that we know that the magnitude of z is constant. Okay? And we know some property of this function, this analytic function. Just say that all the function value have the same magnitude. Then, and turns out that there is no other choice. The function actually is a constant function. It's a constant function in the whole domain. So the proof is that suppose we express the analytic function, which is analytic, okay? Alright, and so this we know, and we know that u square is a constant. Right, so we know that this one, the second thing, that two things, that f of z is analytical in D, and we know that the magnitude is constant. Okay, so now from this equation, from here, because this is an identity. So when we take the partial derivative with respect to x, we know ux and u2 plus 2v x and v is equal to 0. So we have that. And also when we take the partial derivative with respect to y, we know it's 2u1 u plus 2v1 v is equal to 0. Okay? Now, for here, we know that because it's analytic in D, so we know that ux is equal to v1, and we know u1 is equal to minus vx. This is Cauchy-Riemann equations. Okay, so we know that ux is equal to v1, and the uy is equal to minus vx. Alright, and so together, by the substitution, we know that u and the ux minus v and u1, okay, equal to 0. And for here, we have u1 plus v ux equal to 0. Okay, so just do the substitution, because vx is equal to minus uy, and the v1 is equal to ux here. Okay, so together we have, so when we multiply, because we have uy here, right? So we want to something, so we multiply with u. So we have u squared ux minus uv uy equal to 0. And here we multiply with v. So v uy minus v squared ux equal to 0. And then you add these two equations together, you will cancel this term. Okay, and so finally you have u squared plus v squared and ux equal to 0. Okay, so now if u squared plus v squared, because we know that is k squared. If this is 0, then we know u equals 0, is 0. And hence, f is equal to 0. Okay? This is one choice. So f is a constant. If u squared plus v squared equal to k squared not equal to 0, okay, so not equal to 0, so we have ux is equal to 0. And similarly, u1 is equal to 0. Okay. Because we can do this, we can cancel the other way. Okay? Because this algebraic manipulation is to get this one, but we can get the similar expressions. Alright, so we can have ux equal to 0 or y equal to 0. Also, from that, vx equal to 0 and v1 equal to 0. Okay, so this implies that u is constant and v is constant. So this implies f is a constant. Okay, so we have these two because we cancel u1 in this way, but we can cancel ux, right, by multiplying. For example, you can multiply and v, okay, minus v here, and multiply with u here, and add them together. Okay. So let me say, when you multiply with minus, and you multiply u here, you will cancel these two terms. Okay, and then you have what you have. You will have the same, right? You have this expression. Okay, and so you get the similar things there. Because once you know ux is 0, uy is 0, the only choice is u is a constant. And by integration, you know that. So this is just a simple example to illustrate that. If f of t is an analytic function, and you know some information about f of t, for example, you know that this function has magnitude always equal to k, a constant. This is an additional information. Then it will give you a very, very specific result. For example, here the f of t should be a constant function, no other choice. Okay, so some partial information of the analytic function will imply a lot of information. This is a typical phenomenon in complex analysis, and it's very good. Why? Because in analysis, when we come up with the complex functions, we sometimes know some property about the function. But when we know it is analytical, then there's a lot of theoretical result give us saying that, well, this kind of analytic function has a very nice property or some specific strong property. So weak property will imply strong property. The kind of amplification things. So this is power of an analytic function. With polar form, we know we can express a complex we know we can express a constant number in polar form. So now, with polar form, the f of z becomes to u r x theta plus I v r theta. So we will put here. Okay. So we just do the coordinate transformation. Okay, we'll do coordinate transformation. So originally we have u x y, v x y, but we can change the coordinate. Alright. So this is why we are talking about the polar form. In this case, the Cauchy-Riemann equation, right, become here u to r 1 over r v to theta, and the v tilde r is equal to r minus r u tilde theta. Okay, so you can check it because we know how to do coordinate transformation, right? In the previous chapters. So I ask you to verify. So please verify. Okay. So sometimes it's quite useful to use the polar coordinate system. Okay. So this is good. And before I state the next theorem, I would have to give a remark. Okay. We shall prove that the derivative, okay, the derivative f z prime of an analytic function in a domain D is also analytic. It's very strange. An analytic function, sorry, f of z in the domain D. So we know when we say a function is analytic, we mean that its derivative exists, right? In the whole domain, right? Now, the derivative is also a complex function, right? So it's f prime z is also a complex function. And this function is also analytical in D prime. I.e., f prime z exists at all points in D. Okay. So if fz is analytical, then f prime z is also analytical, and then f double prime z is also analytical and continue to infinity. So if a function is analytical, then f has any order derivative. Okay? We will prove, and this needs some manipulation. Okay, so we will do that. in later chapters. Right? But here, I just write to make such a remark, because we need to write down a theorem which is very interesting. If f of z ux1 plus I vs1, okay, is analytical in the domain G, then both u and v, both u and v, right, satisfy Laplace equation, i.e. the square of the gradient, actually we know is uxx plus uyy equals 0. And then the gradient of u will be vxx plus vyy equals 0. u. I think I have to say first, the first view, okay. I think U and V have continuous second order partial derivatives. And satisfy the Laplace equations. Then U and V and V. But so for here, so let's go back to here. F from z is equal to ux plus I vx, or you can write this vy minus I uy. Okay? And because this one, as we will show, this function, this complex function, is also analytical. Right? It's also analytical. So that if I write using this one, okay, in the first pair, so we will have u x x, okay, as I v of x x, or again is equal to v of xy minus I u of xy. Okay. That is one. If I use this one, I change the color. This is our u, right? So we have u and x, and then I, we have U on X. Or we will use that minus U y1, okay, or and then minus I y1. So these two from here, and these two from here. You just have to be patient. Okay? Know that which one you should choose. Okay? So you can just think about that we are using this one. Okay. Because here we have, if you like, okay. So if we choose this one, this is our U, right? U. This is our U, right? Ux here, right? This is our Vx here. Okay? Now, for here, we should have Vy, right? So V1. And the minus this U, right? Uy. Minus Uy, right? And you compare them, you will see that this must be equal to this one, right? So you will see Uxx must be equal to minus Uyy. And also, you compare them, you know Vxx equal to minus Vyy. So you get automatically what? The two Laplace equations. And you will have continuous second order partial derivative. Here, you just say that they have second order partial derivative, right? But because f double prime have derivative again, right? Right here, because if you can apply the statement, f double prime z is an analytic function, so it has derivative. It has derivative. So that U has any derivative, any order of partial derivative. And V has any order of partial derivative. So that's why the second order partial must be continuous. Okay? Must be continuous. So just illustrate why these two, this is, we got the Laplace equations. It is because just you iteratively apply the same result. Okay? You use the Riemann-Cauchy equation again and again and again. And then you can end up with a lot of equations. Okay? And these two, the Laplace equation, just two from many different equations. Okay? Many different. So the Cauchy-Riemann equations very important in complex analysis. They are very simple. They are very but important. Okay. Unfortunately, you just only need to memorize these two simple differential equations, and they are both first order. Right? It's very simple, okay? And you can derive a lot of things, Okay. I think I have. I'm sorry, I haven't given you a prize. Truly sorry. So I have some time, and I want to mention how to use this theorem to construct complex exponential function. Okay, and the rest of you, the rest of the chapter 13, I will let you to read it. Okay. So actually, you have some tools at hand. The tools, the most effective tool is the Cauchy-Riemann equations. Okay, so please remember these two equations. Let me say something about the exponential function. All right, so we want, our purpose is we want to define complex exponential function. Says e to the z, okay? With properties which generalize the real exponential function. Okay, this is our purpose. Just want to do this job. So the specification, just like we want to create a program. So now we want to invent a function. Okay, and so we need a specification, right? So specification, first one is that, okay, this, because it's a generalization, an extension, so there must be the set. If the complex number z is just a real number, then there must be the set. Okay? This is the first requirement, right, for extension. The second thing is we want the function is very nice. So a of z is analytical. Okay? In C. Because we want to define, because e of x exponential function defined on the whole real line. So we want to define a complex exponential function, which is also defined on the whole real line, in the whole complex plane. Okay? And we want that it is analytical. We want it is analytical. Okay? It's very important. Okay, and the third specification is that we want the derivative is the same. Okay? Because the derivative of the real exponential function is the same, right? So we want to keep the same differential behavior. Okay? And the fourth thing is, of course, we want the famous formula, right? If we have a sum of the common number in the exponent, then it will come to the product of respective exponent. Okay, I think we want too much. Okay, I think that would be enough. Good. For all V1, V2. Okay. I think the fourth requirement would be enough. Okay, that's good. So now Now we will see, I think there's nothing to say, right? It's just a requirement, extension. So, so for 2, so let's see the consequences. So from specification, so now for 2 given 2, right? Let me see, given 2. Okay, so we okay, maybe it's too rush. All right, I just stop here. I will continue on Thursday. Okay, so according to some reasonable specifications, we want to know the definite formula for the complex exponential functions. I think these specifications are quite reasonable, right? The extension. We ask it is analytic, and we want this one. I think that's reasonable because we want to keep the real generalization to here. So this is very essential, and we want this is true. I think that is because this is the property we use a lot, right? In mathematics. So we keep the 4 specifications here. Okay. So, and I think at the weekend I will send you 2 notes. One note is chapter 14 and chapter 15. But I ask you to read the first section of chapter 15 about the series sequences, because that I know you learned some sequence and series in calculus. Okay, most of them may be in real functions. Okay, but if we extend to the complex functions, we still need something for the real sequence and the real series. All right, and so I wrote a supplement. It's a little bit lengthy because I want to give you a complete exposure, okay, what's going on, and I write down almost every nice properties to identify the convergence of series. All right, some tests like you still remember the root test, the ratio test, things like that, right? And so I tried myself to compile a supplement for you. So please, at the weekend, read the section 15.1, okay? 15.1. A little bit ahead of that, but we need that stuff because I don't want to spend time on this subject. Otherwise, we cannot finish. We're already late from my schedule, but I don't want it late too much. Okay. Okay. So thank you, and I'll see you Thursday.